Hello everyone, I am Professor Neha Dikshit going to explain you some concept regarding the isoparametric element. It is the part of your 4th unit of finite element subject. In this, see first of all concept of isoparametric element and what is the need of isoparametric formulation. Before going to this unit, in first 3 units we already seen the 1D and 2D elements, and in that we already seen the some rectangular elemental geometry and triangular element geometry. In right hand side figure you can see that one elements are there, and that element consists curve boundaries, and that continuum is divided with the help of the rectangular element in the first figure, and second figure in that meshing is done with the triangular element. So what is happened here we will see later. Now first of all, what is the isoparametric element? Isoparametric is the meaning of that isoparametric word is same parameter. In this, shape function used for that isoparametric function is itself interpolation function. So the term isoparametric is derived from the use of same shape function n to define the geometric shape as are used to define the displacement within the shape, within the element. That is, what is the meaning of this statement? In isoparametric element, if you are using shape function n to define the geometrical shape, then it is same can be used for the to define the displacement within that element. So rectangles. So now we will discuss on these two figures. Rectangles, when you are using the rectangular element to discretize this continuum, then rectangles leave lot of vacant area near the curve boundaries which can lead to the error, and also they introduce sharp corners which results in actually not present in the geometry, and because of that artificial stresses are generated. And if you are using the triangular shape function, triangular elements to discretize any continuum, then aspect ratio of triangular elements are poor at origin. So when aspect ratio is low, then your accuracy of the result is increases, and when aspect ratio is poor, that is a higher, then the results are results contains. So, combined use of both rectangles and triangle can introduce discontinuities at boundaries, thus affecting the compatibility. So, to solve this problem, we use general quadrilateral whose angle are not restricted to 90 degrees and they fill curved domain with satisfactory aspect ratio, and that elements are known as the isoparametric elements. The isoparametric formulation make it possible to generate elements that are non-rectangular and have curved sides. So, it can facilitate an accurate representation of irregular elements. So isoparametric element, this is the isoparametric elements, curves are present and angle is not restricted to the degree. Next, what is the use of isoparametric element? Isoparametric formulation is generally applicable to the 1, 2 and 3 dimensional stress analysis. The isoparametric family includes elements for plane, solid and shell problems. Also, it is applicable for non-structural problems. Now we will see derivation regarding the quadrilateral isoparametric element. Before that derivation, we will see the basic shape functions using the Lagrangian polynomial. Lagrangian formulation we can use to derive the polynomial. So first of all, we will see isoparametric formulation for bar element having the two noded, but it is in natural coordinate. So consider this bar and having the two nodes, that is the x0 and x1, and we are seeing this derivation in natural coordinates. So natural coordinates lies between -1 to +1. So your x0 coordinate value is -1 and x1 coordinate value is 1. Suppose we want to derive the coordinate value for the x, then according to Lagrangian polynomial, shape function n1 is equal to L0 is equal to x minus x1 divided by x0 minus x1. But what is the value of x? X is arbitrary any coordinate having the coordinate zeta. And what is the value of x1? Value of x1 coordinate is 1. So zeta minus 1. Now what is the value of x0? X0 is -1 and x1 is 1. So zeta minus 1 divided by minus 1 is equal to 1 minus zeta upon 2. Next, second step function, same, using the Lagrange's polynomial, is equal to L1 is equal to x minus x0 divided by x1 minus x0. Now here x is again zeta, x0 is minus 1, minus of minus 1 divided by x1 coordinate value 1 and x0 coordinate is minus 1. So 1 minus of minus 1. So your n2 is 1 plus zeta upon 2. So if you want to calculate the x coordinate, and you will have x1 and x2 also shape function n1 and n2, that is the 1 minus zeta upon 2 and 1 plus zeta upon 2 respectively. Then in matrix form you can rewrite as x is equal to, in matrix form, first row is 1 minus zeta upon 2 and 1 plus zeta upon 2 into multiply by the matrix in a first row x2. So this is the isoparametric formulation. Next is Lagrangian rectangular element. Consider a square element of side 2 units with a center at origin as shown in figure. So this is figure and this one is the rectangular element while its center is origin. So according to that, the 2D shape functions are obtained using following steps. See, in this rectangular element center is equal to origin. So 2 unit length is there for this rectangular element and this is the first coordinate. So obviously this is center, then it's minus 1 dimensions are there. For the second coordinate, obviously positive x sign, so plus 1, and negative y sign minus 1, and third coordinate is positive for zeta and eta 1 and 1, and fourth coordinate is negative for the zeta and positive for the eta, so minus 1 1. So consider for the coordinate 1 minus 1 is zeta 1 eta 1, second coordinate zeta 2 eta 1, third coordinate zeta 2 eta 1, and fourth coordinate zeta 1 eta 2. Obviously zeta 1 is equal to minus 1, zeta 2 is equal to 1, eta 1 is equal to 1, and eta 2 is equal to 1. Sorry, eta 1 is equal to minus 1 and eta 2 is equal to 1. So for zeta coordinates Lagrangian polynomial, that means for zeta coordinates shape function n1 is equal to 1 minus zeta upon 2 and 1 plus zeta upon 2. Two shape functions for the zeta coordinates and for eta coordinates 1 minus eta upon 2 and 1 upon 2. This is we already seen. So shape functions at the nodes by multiplication. So at node 1, n1 is equal to, it is the multiplication of the combination of the coordinates zeta 1 and obviously eta 1. So put the values of zeta 1 and eta 1. So your equation is 1 minus zeta into 1 minus eta upon 4. This is the shape function at node 1 n1. Next is at node 2, n2 is multiplication of zeta 2 into eta 1. So put the value of zeta 2 is 1 plus zeta upon 2 and eta 1 is 1 minus eta upon 2. So your equation for the n2 is 1 plus zeta 1 minus eta upon 4. And same for the n3, it is the multiplication of the zeta 2 and eta 2 combination. So your n3 is 1 plus zeta 1 plus eta upon 4. Same for the node 4, n4 is equal to, it is the multiplication of zeta 1 and eta 2 combination. So 1 minus zeta 1 plus eta upon, we get the conversion of the local to natural and natural to local coordinates. Next we will see one example on quadrilateral element, that is the isoparametric formulation. See here, a quadrilateral element is defined by 1 4, 4 2, 5 6 and 2 7. The temperature at nodes are 20 degrees Celsius, 30 degrees Celsius, 40 degrees Celsius and 25 degrees Celsius. Find the temperature at point P 3 and 4. And second is find the isoparametric formulation and Jacobian matrix. See here, one quadrilateral element is given. Figure is not given in your example. You have to draw that diagram according to given coordinates, and coordinates are given. First coordinate is x1 y1, that is the 1 4, and temperature on that node is 20 degrees Celsius. Second node is x2 y2 is equal to 4 and 2 coordinates given, and temperature at node second is 30 degrees Celsius. At node 3, this is the 5 and 6 coordinates are there, at node 3 and temperature at node 3 is 40 degrees Celsius. At node 4, x4 and y4 coordinates are 2 and 7 is given and temperature is given, that is the 25 degrees Celsius. So now see here in this numerical you are having the temperature at individual nodes and coordinates of the individual nodes, but no shape functions are given and one interior point is given, that is the P34, and you have to calculate the temperature at that point P. So according to given condition, shape functions in natural coordinate, this is the n1, n2, n3 and n4 for the quadrilateral element. So according to isoparametric formulation, x is equal to n1 x1 plus n2 x2 plus n3 x3 plus n4 x4. We know the x, that is the P point, okay, but we will put the value of that x in later and put the value of n1, n2, n3, n4, expand all brackets, you will get x is equal to 12 plus 6 zeta plus 2 eta divided by 4. Same y, put the value of n1, n2, n3, n4, put the value of y1, y2, y3, y4 and expand all this bracket. Don't put the value of y, we will put later, and y is equal to, you will get equation 19 minus 3 zeta plus 7 eta plus zeta into eta divided by. So Jacobian of transformation we already seen before, that is the J matrix is del x by del zeta, del y by del zeta, it is the first row, and second row del x by del eta, del y by del eta, it is the second row. So you know the x and y value and partial derivative of with respect to zeta and eta, putting the value of x and y, you will get 3 by 2 minus 3 plus eta upon 4, 1 by 2 and 7 plus zeta upon 4. It is next, natural coordinates zeta and eta corresponding to the global coordinates. See, global coordinates we already know the point P, 3 and 4. So x is equal to 12 plus 6 zeta plus 2 eta divided by 4. Expanding the bracket we will get, we already get this equation is equal to 3 and y coordinate is 4, and for that equation we already get previously 19 minus 3 zeta plus 7 eta plus zeta eta upon 4. So first of all we will treat the x coordinate. So expanding the equations, you will get eta is equal to minus 3 into zeta. So you will get a eta value instead of the zeta, and expand the y equation and you will get here 19 minus 3 zeta plus 7 eta plus zeta into eta is equal to 16, and put this eta is equal to minus 3 zeta in this equation and you will get one quadratic equation, and roots of that quadratic equation is zeta is equal to 0.123 or zeta is equal to minus 8.123. Now we have to choose one for the zeta value, but we already know that natural coordinates lies between the minus 1 to 1. So obviously minus 8.123 it's a wrong choice. So we have to choose zeta is equal to 0.123, and as zeta is equal to 0.123, so eta is equal to minus 3 into zeta, put the value of zeta, you will get eta is equal to minus 0.369. So put the value of zeta and eta and you will get n1 into n3 and n4. Next is temperature. Using the isoparametric formulation, temperature at point P is equal to n1 T1 plus n2 T2 plus n3 T3 plus n4 T4, and you have the values of n1, n2, n3, n4 now, and also temperature at node 1, 2, 3, 4, that is the T1, T2, T3 and T4. So calculate, put the values and calculate the temperature, that is the 28 degrees Celsius. So temperature at point P3 and 4 is 28 degrees Celsius. Thank you for the listening.